sum, say, k equals n plus 1 to infinity of rho f ij of the n to the n to the kth power, the ij's term is less than or equal to the sum k equals n plus 1 to infinity of rho max n. So basically this is the fact that this series is dominated by this geometric series. Really we should have absolute values in general, but all the terms here are non-negative. And who knows what this adds up to? Remember the formula for the sum of a geometric progression? If you add infinitely many terms, it's the first term you're adding, which is rho max n plus 1 divided by 1 minus the ratio, rho max. And the way you prove it is basically just the same proof I had last time. You multiply the answer by 1 minus rho max, and all the terms cancel except this one, because you're canceling off toward infinity. So basically, if rho max is significantly different from 1, this denominator isn't so tiny, and these powers are going to 0. So you can figure out this number of max iterations. I don't know if I spelled it out or just called max iter in the loop last time, to be some number which is relatively small compared to n, with the number of patches. Maybe this should be capital N. This is the number of patches, and this is the number of iterations I want to stop at. So instead of O capital N's cubed, the iterative method takes time O capital N squared, because each iteration had, this should have been capital N squared times max iter. Okay, so this could be a relatively small number compared to capital N, and so this iterative method will be faster. So now I want to make the interpretation of form factors in terms of power. So the power leaving surface SI, and that's PI. It's the power per unit area, which is the BI, multiplied by the area. So if we take the basic equation that the radiosity satisfied, this is sort of equivalent to our integral equation, only we discretized it by the finite elements. We had BI equals EI plus rho I sum form factors times the Bj, and we multiply it by both sides of the equation by AI. We'll get AI Bi equals AI EI plus rho I sum J F I J A I B J. And now by reciprocity, this is the sum F J I times A J. And the rest of this is going to be the same. And so this is the power on I. This is what they call the power emitted on I, this product, plus rho I, the sum over J of F J I times the power on J. So what you could think of is Fji is the fraction of the power leaving surface J that ends up on surface I. Then you multiply that power by the reflectivity, and you get, because this is diffuse, the rho is sort of the fraction, the power that's reflected, and you get the power coming off of AI after we add up all those contributions. So we can do an alternate iterative method which says we'll initially start the pi of 0 for all I as this PEI, which is the emission times the area. And then basically pi k plus 1 equals PEI. This is all for all I. We're going to do this sum here. Fji, I guess, times Pj to the k. So basically, because, you know, this basically by this derivation is the same as this one, which was in my previous iterative loop. This is exactly the same algorithm, it just, you know, temporarily multiplied by all the areas. Where it can be improved is by instead looping this says for all, this outer loop is on I. You know, I just wrote this formula, but there's an implicit outer loop on I in each of these formulas, and inside there's an inner loop on J, like we did before. But we can reorganize it and say, for a patch J, add its contributions to all the other patches. So that the outer loop will be on J and the inner loop will be on the other patches. And the advantage of doing it that way, that's sort of shooting the power off of the patches, is that you can shoot the power off of the patches like the light sources that have the most power there first. And then maybe the walls and the floor, because they're big and they're well illuminated, shoot them before you bother shooting the light off the chairs, which are dark and small. So you might get several reflections off of the walls before you even bother to do any off of the chairs or off of your dark black shirts or whatever. So in order to do that, we have to keep track of, so this is the progressive shooting. We're going to keep track of unshot separately from the power that we've accumulated. And the reason is because we're not going to have an even loop where for all the patches J we're going to shoot the power and then we're going to go through them all and shoot the power again. That way we wouldn't be able to shoot the walls twice, so before we shot the chairs. So this sort of counting here isn't going to work. So basically what we're going to do is we're going to initially set PI to be, say, PEI, which is, as I said before, the emissivity times the area of I. This is for all I. But we're also going to set the unshot, the power that we didn't already shoot off into the scene from that patch. That's the new power, you know, for the second time that wall shoots. You don't want to shoot its initial power because you're going to be accumulating the power from each shooting. Equals the same thing, PEI. And now I'll say, while not converged, And so what you might want to do is pick the pick I so that the unshot radiosity is the largest. And whenever you found that largest unshot power was less than a threshold, or you could divide it by the area if you were worried about the colors converging, you would keep going. Otherwise, you would stop and say it's converged. And so you want to shoot that power. So for all patches, why don't I call this one J, because that corresponds to the patch that's shooting the power here. I wonder if that's going to make my notes look different. Probably it is, but let me try it. For all patches I, see if I can do this right now. So the unshot power on patch I equals rho I times F, let's see, the fraction of the jth power that's going to hit power I times the unshot power on the jth patch, plus equals, right? That corresponds to getting one term out of this sum. And now what I'm going to do is set delta, after I do this loop for that patch, I'm going to set delta Pj equal to 0, because now I've shot the power from that patch. So when you're done, it's going to be the sum of all the power. I guess basically what I should do is say Pi, my accumulated power, is also added on this same amount, right? Yes, you could compute it once as a variable and add it on, or presumably your compiler is clever enough to realize the same right-hand sides. And that means now you're accumulating the power, and you can display it at any stage. So inside this while loop, one of the advantages, you can actually watch the picture get better and better as it converges. So you can display with the radiosities Bi equals the power at I plus the extra power that you haven't shot yet. Let's see. No, because I've done it this way, I've been accumulating that power. Whatever power is received, it's already there. Pi over Ai. Right? So the colors are proportional to that radiosity. So you can display so let's see, this is my bracket. And I guess this ends here. At any stage, you can display it. So if you are willing to keep recomputing these form factors each time you choose a shooting patch J, you don't even have to store the matrix of form factors, which means you could have 1,000,000 patches instead of having 1,000,000 squared form factors. You can compute them on the fly each time you do this shooting iteration. And so one method of computing it on the fly is by actually ray tracing from patch J and seeing which patches those rays hit. So you want to pick rays that are, say the patch has constant radiosity, that means constant per unit area, density of the origin point for the ray, and for the direction point, you want them constant per unit area normal to the beam, which means they should be distributed according to the cosine of the angle of the beam with respect to the normal of the surface for shortening factor in computing we got power per unit surface, but we want them, how can I say it? The actual power is going off less by the computed surface area in order to make the power per projected source area be constant, which is what a diffuse surface does when it radiates equal radiance in all directions. So that means we can, for patch J, choose rays, say x theta in AI omega above the normal of the surface. I guess this is where they are. With constant probability probability per area x and it's basically proportional to the cosine of the ray direction and the normal and to the patch. And what they show in the book is that this is 1 over AI is the probability of, because if it's going to be constant per unit area and the area is AI, the density of x per unit area is 1 over AI. And then we have cosine of n theta. It's proportional to that, and the proportionality factor for that part has got to be pi, right? Because the cosine integrated over the hemisphere is pi. And so, you integrate it out, and that's going to integrate out to 1, as they do carefully in the book. So this is the probability density. So how can you choose those rays? Just pick two random calls, say if it was a rectangular patch, which people most often use, to choose a point uniformly per unit area in the rectangle. Or, you could use like 2 barycentrics on coordinates in a triangle, say, and use the cumulative distribution, which I guess is going to involve a square root on one of them because of, the area is proportional to the square as you move across a barycentric coordinate. And, get the random uniformly distributed point, and then I think we already talked about how you get a random distributed cosine weighted ray, because you're going to be using that for your cosine weighted distribution in the next homework to sample the environment. So it's easy to generate such rays, and then you just can compute the form factors using them. So I guess that's what I should verify. Basically, my claim, maybe I should go back to the first board. So these are what the book calls local rays. This board is not erasing very successfully. I don't know if it's the chalk or the board surface, but let me try this one. Has it always been that left board that gives me trouble erasing? Maybe it's made out of a different material. No, now it's the top of this board also that isn't erasing well. Okay, so what I'm claiming is probability of one of these rays starting from patch I, say. I guess I've got, let me keep my notes like this. The probability of starting from patch I and going to patch J is proportional to Fij. So the probability, so this is the probability that a ray shot from patch I hits patch J. So that's going to be the integral of this probability density over the set in my space over on the blackboard, this area of I and omega above the surface, that for which it's true that the ray hits patch Sj. So I'm going to use a slightly different notation than they do in the book, where this proof is right out of the book. Integral over the area of the patch I, integral over this normal above the patch, assuming it's a flat patch, of the probability density, 1 over AI times cosine the angle between theta and this normal divided by pi, integrated with respect to the solid angle of these thetas for the inner integral, and then integrated dAx over the patch I. But that's the probability density. And now what's the event? The event is, I guess, the ray through theta, through starting at x in direction theta is a subset, is some point in Sj. Right? That's the probability. So this is the event that it hits, and we're multiplying it by the probability density, and we're integrating. I should have put that up. Well, this should go over here. dAx. Okay, and now, as usual, we're going to switch to an area representation. So we're going to look at the area on surface J. So here's Si, here's Sj, and now this thing is going to be basically integrated over the area of J, and if the ray gets into that thing, that means it didn't hit something else first. So that's the visibility, say, of between x and y, where x is in here, Si, and y is in Sj. Now we have 1 over AI. We have cosine theta n. Really, this is n over at x. X is on the surface. I'm assuming that it's a flat surface. Over pi. And now we have to have this omega, d omega. We've already taken care of this factor here. This d omega is d a y it's the area times cosine of, I guess it's minus theta ny over r xy squared. That's this solid angle, and then we have dAx. Right? That's just conversion of the angle integration into a area integration that we've done a couple times already. And the fact that the ray hits patch Sj, we're only integrating over directions that do aim at Sj by integrating it this way, but we still have to check the visibility that those rays don't hit something else first. So basically, this much makes the form factor integral by the definition of the form factor that I did last time. So basically, this is, and then 1 over a was outside that integral, basically, when I wrote it last time. But this is basically the form factor ij. Okay, so we can get the form factor just by this probability. So basically, we'll choose, say, ni samples leaving patch well, patch I, now I can see why. See, I shouldn't have changed my notes to J there. And estimate Fij equals Nij over F over Ni, where Nij is the number that hit patch J, that surface J. So this is particularly good for the progressive radiosity scheme because we can use it for any given shooting patch. Here, unfortunately, I've called it J because I was trying to be consistent with this formula, and use that shooting patch with these rays generated, just by sampling this probability distribution by the techniques you're going to have to use for homework, and figure out which patch they hit first and just increment the count on that patch, and you'll get estimates then of the form factors to use in this iteration. You could also, by using reciprocity, use it to estimate the form factors you need for the Gauss-Seidel iteration. Okay, so that's the method of local lines. We sort of started these lines on the shooting patch. Right, here's the shooting patch, and we saw what other patches those lines hit and incremented those counts. Then there's a method of global lines that are presented in the book, which is to compute all the form factors simultaneously by taking a collection of lines that's uniformly distributed in position and direction throughout space. Well, actually, you're only going to use a finite amount of space. Otherwise, you can't generate a number uniformly between 0 and infinity or something. You put a bounding sphere around your scene, and you say, generate all the rays inside that sphere of totally random direction and total random position. And then see which patches they pass through. So you have a sphere around your scene, say of radius r, some bounding sphere for all the objects, and you have a bunch of different patches in this scene. I don't know. Here's a table inside a room and a door or something. Or maybe this is a big shipping box that's inside the room. You're taking these global lines, and every time a line crosses between two different surfaces, you say that corresponds to something that's going to contribute between this patch and this patch. And then that same global line is going to have multiple contributions for each segment of the line between two patches. So to do that, you just change your ray tracing algorithm so it gets you a sorted list of the intersections instead of only the first one. And in fact, if some of you have studied in other courses on ray tracing, these hierarchical structures or grids or bounding hierarchies, so that you're going to get the first intersection first, that's actually going to make your sorting easier, but you're not going to use the early termination that those can give you. You're just going to keep sorting. And so this is global lines. And the method suggested in the book that I actually want to spend the rest of the period talking about for distributing global lines is create this bounding sphere and then generate pairs of points S and T randomly with uniform probability per unit area on the enclosing sphere. So that means on this sphere of radius r, we pick a random point S, we pick a random point T, and we draw that random line. So you can see by rotational symmetry, the direction should be random. And what I want to prove is actually the amount per unit area crossing any surface perpendicular to that beam is going to be constant. You'd think because there was sort of maybe more points here, you'd get more out near the edge, but in fact, because of this slant for shortening, that sort of cancels that effect. So what I want to do, which the book doesn't go into, is a calculation of why this works. So the idea is, so basically, so let me write the words that we do that. So find all segments of the rays between Si and Sj and increment Ni. Each time one of those things hits the surface, you're going to integrate Ni for that patch. And each time it goes from that surface to the next one, you're going to increment Nij. And then, as before, I guess I just erased it, estimate Fij equals Nij over Ni. So why does this method of picking the 2 points on the sphere give this? It's basically what we need is uniform density of the lines per unit area measured perpendicular to the line direction. It's like we have equal radiance flowing in all directions. So this isn't erasing well. Maybe it's the brand of chalk. Or maybe it's the eraser. What shall I do? Maybe this board is better. Sorry for the delay. Let's look at a sphere, and let's look at a dA. Let's see if I've got my picture here. Here and a dB here. Right? That's where I'm choosing my 2 points. So if I fix the first point, say S, basically what I want to do is figure out, because I already know, at least on the sphere, they're uniform per unit area. Right? You can do that, say, by this cumulative distribution on the theta angle measured from the North Pole or something to make them uniform per surface area. I want to know how many I get per solid angle. So if I measure from the center of the sphere, maybe I better make my dB smaller, otherwise it looks like everything is way too big, that I don't have a unique angle. Really, I have a very small angle up to here, angle theta, measured this way, and here is a d theta there. Okay, here's my sphere of radius r. Here's my center of the sphere. Does that look like the center? A little bit over, maybe. This is an isosceles triangle. So this exterior angle is equal to the sum of the two interior angles, which are equal, and so this is 2 theta. Okay, so now what I want to do is I want to look on the unit sphere around S and find an area on that unit sphere d omega of theta. So we know d omega of theta, that hits this patch B. If you knew d theta, it's d theta d phi sine theta. This is not capital theta. This is the theta and phi in polar coordinates with the north pole in this direction. Or I guess this direction, it doesn't matter. I guess this direction. Okay, so what I want is, I want to think of my number of lines as a sort of a flux, right? The integrated probability of all the lines that start here and end there. That's going to be my flux from dA to dB. And so that flux, d squared phi, is really the integrated probability of picking. There's a probability density times dA dB. I guess it's some constant. This is really k squared, right? Where k is the probability per unit area. So let me think. K equals 1 over the total area of the sphere, which is 4 pi r squared. Let me think about that. Let's just assume it's a constant. I think I'm okay with the constant. I'm wondering if I have to square this because I've got a dA and a dB here. Whatever it is, it's some proportional to the area dA and dB. It probably is this thing squared. And now what I want is d squared phi and I want to know is how many lines I'm going to get. The number of lines if I integrate this probability and multiply it by capital N, the total number of lines I'm shooting, I'm going to get the expected number of lines in here. And so I'll call L as its expected number of lines. It's sort of like the radius, because it's expected number of lines. Really, the total number, if you think of this as a number of lines, then this thing is going to be the number of lines d squared phi over cosine theta, because theta is the angle between the normal to the surface and this range, and that's the foreshortening factor per unit area normal to the beam. So I multiply it by the area of A normal to the beam, and I also divide by the solid angle. The solid angle is the solid angle of B going to the point S. This is dB, right? And this is N d squared phi. Well, I already have an N here. If I'm going to put the N there, I don't need it here. This count, let's see, times this solid angle is this is cosine theta here, dA, and the solid angle I have let me think. What I can find this angle here is twice d theta, right? Because it's if this angle was twice that one, and this angle is twice that one, then this is twice the difference here. And now I have to multiply for the what I want to say is dB is twice d theta, that's this angle, times r, now so I'm not my unit radius anymore, I'm my capital radius, r sine 2 theta times let me think, times d phi, right? Because d phi is still going around the sphere the same way. The d phi of this little piece is the same as the little d phi of that little piece. And what I'm trying to do is relate the area of dB to this theta. So what do I have here? That means d omega s from dB to s is the area dB times the cosine, let's see, why don't I just call it cosine of this minus theta, which is my ray direction compared to n at the point t that I'm choosing here, divided by rxy squared. Let's see, no. Yeah, that's right. And so let me think about this. What I want to show is this comes out independent of the direction. So have I done this correctly? What I want to put here is nk dA dB, and in the denominator I have cosine theta dA, and I have this one is going to be cosine minus, well, let me think. I think I'm messing myself up. I thought I had understood it all. What am I trying to find? I'm trying to find out what's the amount. I'm trying to show that the amount per solid angle is a constant. And for here, I want to say this is what I'm trying to Okay, so for dB, I'm going to write, I guess, this one, 2 d theta times r times sine 2 theta is 2 sine theta cosine theta and then I have, and wait a minute, is this to go in the numerator or denominator? I'm totally confused. I had this all figured out before class. What do I want to show? I want to show that this thing is constant, independent of what direction you get on the sphere. So, I guess this angle is the same as the angle between the normal and the direction here is the same as the normal and the direction here because these two cosines are the same. So, if I have I'm dividing by d omega b, I have this is my dB, no, d phi. I've got my 2 d theta already, d phi. Means I get rxy squared. I mean, if I'm dividing by that, this should be in the denominator. Okay, I'm out of time. I'll try and finish this next time or send you email. I convinced myself before, and now it's not working, that this does, the foreshortening does give you constant per solid angle normal to the beam. So let me finish that next time. Sorry for not figuring out what I had in my notes.